In this video, we're going to look at the unit circle and trigonometry, and in particular how trigonometry, which is all about right angled triangles or other triangles, is actually linked to a circle. So first of all, we're going to have a unit circle here. It's a unit circle because the radius is 1. So it goes up to 1 and minus 1 in both directions, x and y. It's a unit circle. And what we're going to do is we're going to look at what happens when we draw a point. We want to pick a point on here. So we're going to pick a point, and we're going to actually pick this point here. We'd like to know what is the coordinates of those points, that point there, or any point on the circumference of the circle. And the way we do this is actually we think about the line that goes up to that point there. And as you can see, this line here is going toward a point, which means that this angle here is 45 degrees. But once we've drawn that thing, we can actually draw two other bits going across the x-axis and going vertically up to that point. And now we end up with a right angled triangle where the angle is 45. So the point that we were originally interested in has coordinates the length along that blue line at the bottom and the length along that blue line going upwards. So let's call this one here x and this one y. That means this point here has coordinates x, y for those values of x and y. So can we find those values of x and y? Well, one thing we need to remember is this triangle is in a unit circle. So the green length is the radius of the circle. So the green hypotenuse of the triangle is 1. And now we can see we've got a right angle triangle, so we can use some trig. Now x is the adjacent and y is the opposite. So first of all, x, well, that's the adjacent hypotenuse, that's cos. So what we know is that cos of 45 is equal to the adjacent x over the hypotenuse, which is 1. Similarly, we have that for the opposite, we have sine of 45 is equal to the opposite, y over the hypotenuse, is 1. So what that means is that x is equal to cos 45 and y is equal to sine 45. But we can be a bit more general than this. We can change, instead of using 45, we could say we don't use 45 anymore, we're going to call this angle theta for the general result. And the exact same thing holds true. All we do is every time we have 45, we replace it with theta. So now cos theta is equal to x over 1. Sin theta is equal to y over 1. So x is equal to cos theta and y is equal to sine theta. And this is how we have trigonometry embedded within the unit circle. So let's have a look at how we could use this and how this relates to the graphs. So on the left here we have the graphs of our three trig functions. The first one is y equals sine x. So let's look at this first. The first thing we notice is we're going to look at each sort of quadrant of the circle. So we're going to split the circle up into 4 pieces. And remember, when we were looking in the previous one, we always started here and our angle went round this way. And that's also always true. We always go around in this anti-clockwise direction, going around the circle. Get rid of that. That's way ahead. And we're going to look at each part of this graph of sine. Well, in the first part, between 0 and 90, sine x the value we get out of sine x is positive because it's above the x-axis. So in this section here, this is 0 to 90, we have that sine x is positive. Now we keep going and we look between 90 and 180. Well, 90 was this vertical bit up here, and 180 is if we go half a turn around to here. So that's 90 to 180. And once again, the graph is above the x-axis, so sine is positive. Now we're going to do between 180 and 270, this bit here. 180 and 270 is this bit here. But this time the graph of sine is below the x-axis, so sine is negative. And finally, between 270 and 360, between 270 and 360, we see that sine is below the x-axis, so again it is negative. Now we can do the same with the other two as well. Y equals cos of x. Now the first part between 0 and 90 is above the x-axis, so between 0 and 90, cos is positive. Between 90 and 180, between 90 and 180, this bit here, in green, cos is below the x-axis, so it's negative. Between 180 and 270, between 180 and 270, cos is below the x-axis, so it's negative. And finally, between 270 and 360, between 270 and 360 in our unit circle, cos is above the x-axis, so it's positive. Finally, our third trig function, y equals tan of x. In the first bit, between 0 and 90, between 0 and 90, it's above the x-axis, so it's positive. Between 90 and 180, between 90 and 180, it's below the x-axis, so it's negative. Between 180 and 270, 180 and 270 is above the x-axis, so it's positive. And finally, between 270 and 360, between 270 and 360, it's below, so it's negative. And we can put this all together into one diagram. We have the quadrants. We don't actually need to draw the circle each time. We're just interested in the quadrants. Now if we look at this, we see that in what's called the first quadrant, that's between 0 and 90 in blue, all of them are positive. If we look in the second quadrant, that's green, the top left, we see that only sine is positive. If we look in the third quadrant, that's the red ones, we see that only tan is positive. And finally, if we look in the fourth quadrant, that's the purple one, we see that only cos is positive. And we get this 4 letters in the quadrants here that tell us what is positive where. Remember, that means sine, all of them, tan and cosine are positive on those letters. There are lots of ways to remember this. One of the traditional ones is cast. I don't like cast because it doesn't start in the first quadrant. The way that I like to remember it is the way we read, which is using a very famous TV show, Sex and the City, tells us the order that those 4 trig functions, or 3 trig functions, and all the positive ones go in that quadrant diagram. So how can we use this? Well, we can use this to solve equations, trigonometric equations, and we can also use it to find the values of some trig functions of different values. So let's have a look at the first one here. Without using a calculator, find the value of sine 240. And there's 2 ways we can go about this. We can use the quadrant or we can use the graph. I'm going to show you both, and you should choose which one you prefer. Most people prefer the quadrant, that's the one that most people prefer, but you should be able to use the graphs as well, but use which one you find easiest. So for sine 240, the first thing we do is we think about our quadrants. We have sets and the city. And we think about where 240 degrees is in that. Now remember, we start at 0 along here. So this one up here is 90, 180, and 270. 0. So 240 is coming down here. Whenever we use the quadrant rule, we are only interested in how far away it is from the x-axis. So how far is 240 away from 180? Well, that angle there is 60 degrees. Now this is what we do. Now we know that, we do sine 240 is equal to, well, we know that sine is negative down there, so we know it's going to be negative, and it's equal to the same value as sine of 60, but negative. But we know sine of 60 from our exact values is root 3 over 2, so sine of 240 is minus root 3 over 2. The other way to do this is using the graph. We think about the sine graph, that's this. We've got 90, 180, 270, and 240 is about there. Different colours so it's easy to see. 240 is there. So we're interested in the value, that y value there. To find that we use the symmetry, and again we see from there we have 60, and because that point is where it crosses the axis at the root, we go from here, and it's the same as if we go 60 out there, and we can use the graph that way. And we get the same result. It's negative because it's down here, so it has to be minus, and it's the same as sine 60. Have a go at the next one, tan of minus 45. We draw a diagram, 0, 90, 180, 270. Minus 45, so this time we're going minus angles, which means they go the opposite direction. So minus 45 is actually 45 down here. So this angle here is 45. And that's the angle we want, because we always want the angle from the x-axis. If that's sine 45, or sorry, if that's 45, we'll look at the tan of that, while tan of minus 45 is equal to, well, it's in the C quadrant, the cos quadrant, so tan is negative, so it's definitely negative, and it's just equal to tan of minus tan of 45, because 45 is the distance from the x-axis. So that's equal to minus, and tan of 45 is 1, so it's just equal to minus 1. Again, we could have done this using the graph. This time we have to go a bit out that way, and the tan graph does this, and then it carries on, but we're only interested in the first section. At minus 45, that's there, it has the same vertical value as if you went up at 45 and went across, but it's negative. So 45 will give us 1, so minus 45 would give us minus 1. Finally, cos 330, once again, we draw our quadrant diagram. And we're interested this time in 330. 330 is almost all the way back there. And this time if it's 330, then it's 30 away from a full turn of 360. So the angle there is 30 from the x-axis. Remember, it's always from the x-axis. Get rid of that box surrounding that. And now we can go cos of 330 is equal to, well, cos is positive in that quadrant, so it's still positive. We don't need the negative this time. And the angle it's equal to is 30. So cos of 330 is the same as cos of 30, and cos of 30 is root 3 over 2. Again, using the graph, we could have done the same thing. Cos looks like this. This is 360 at the end here. Just about to squeeze that on. Then 330 comes up here, and that has the same value if we went across as 30, because this distance here is the same as this distance here. So that's how we use the unit circle and the section of the city diagram or the cast diagram to find exact values of trigonometric functions that are multiples of our normals 30, 45 and 60.